Okay, this video is going to be on how to derive the geometric mean, and then I'll make another one on how to solve problems with it, and a final one on how to derive the Pythagorean theorem with it. So what is geometric mean? Let's go back to like when you did arithmetic and geometric sequence problems. So an arithmetic sequence is something like 2, 5, 8, 11, and so on, where you basically add the same number every time, adding 3 to this one every time to get the next number. That's an arithmetic sequence. Lots of stuff you can do with this, but we're going to do just a little bit just to draw a contradiction or a comparison of the two. So in an arithmetic sequence, the middle number is the arithmetic mean of the other two. 8 plus 2 over 2 is 5. That happens in all arithmetic sequences. They can be addition or subtraction. So generally speaking, if you have an arithmetic sequence, A, B, C, and so on, and our common difference, or the number that gets added every time, is, let's say, x, we know that A plus x equals B, and B plus x equals C. Now, if I solve this for x, x is equal to B minus A. And if I plug that in for x in the other expression, b plus b minus a equals c, 2b minus a equals c, 2b equals c plus a, so b equals a plus c over 2. Just again, showing that the middle term is the arithmetic mean, or the average, of the first and third term. This happens for any 3 terms in the sequence. 5 plus 11 is 16, divided by 2 is 8. If I add another term, 8 and 14 is 22, divided by 2 is 11. I get 28, divided by 2 is 14, and so on and so on and so on. So we have an arithmetic sequence leading to an arithmetic mean. Now let's look at the geometric sequence. We'll finally get to the geometry. A geometric sequence is one in which you multiply something every time to get the next term. So for example, if I start with 3 and I double it, and then I double it, and then I double it, and so forth and so on. In a geometric sequence, you don't add 2 terms and average or take the mean to get the one in the middle. You multiply 2 terms and take the square root to get the one in the middle. 6 times 24 is 144. The square root is 12. 12 times 48, the square root is 24, and so on and so on. Now if we want to do this generally speaking, to get to the formula that we're going to walk away with, we have that if we have a geometric sequence, I'll use A, B, C, and so on, you multiply by x every time to get the next term, and x can be a fraction, which would indicate a sequence in which you were dividing every time. Then I would know that A times x equals B, and B times x equals C. This would imply that x is equal to b over a from the top equation. If I plug it in here, I get b times, instead of x, I'm going to put b over a. So now I have b squared over a equals c, or b squared equals a times c, or b equals square root of a times c, which takes us back to here. In a geometric sequence, given any 3 consecutive terms in the sequence, the middle is the square root of the product of the other 2. So for A and B and C, B is equal to the square root of the product of A times C. There it is. So that is called a geometric mean, a different way of averaging. So now that we have those set, let's talk about how this plays out in a right triangle. The goal is for you to walk away with the two geometric mean theorems. I'm going to tell you what they are, and then I'm going to derive them for you using some simple proportions. So we have a right triangle. We drop an altitude to the hypotenuse. Let's call that altitude F. Okay. The two theorems we're going to walk away with are the altitude geometric mean, which says the altitude is the geometric mean between the two segments of the hypotenuse. So we're going to end up with that. Then the other one says each leg is the geometric mean. So the leg is the geometric mean. In this case, let's use the leg of A, between the length of the entire hypotenuse, C, and the segment of the hypotenuse adjacent to that leg, D. If we do this for the other leg, B, it's the geometric mean between the entire hypotenuse, C, and the segment of the hypotenuse adjacent to that leg, or connected to that leg. See how it's connected there? E. This is the two theorems we're going to come back to. Let's take that same picture and play what I like to call the three little bears. Same picture. We're going to break it down into the three right triangles. Okay? We have the big one, which has a short leg of A, a long leg of B, a hypotenuse of C. We have the medium one, which has a long leg of E, a short leg of F, and a hypotenuse of B. And then the baby one, short leg of D, hypotenuse of A, long leg of F. These triangles are all similar by angle similarity, because if you look at the big one, let's make this a one arc angle and that a double arc angle. So between A and D, A and C, sorry, the big hypotenuse, this is going to be the larger angle. This is the smaller one. And the medium triangle, that angle is here. So this angle has to complement it. So it has to be the same as the other angle over here. And then in the little triangle, this angle complements the other one. So we have angle similarity playing out in the three similar triangles. So I'm going to make every possible proportion I can make. I'm going to forget about this picture and just focus on these three triangles and make all the proportions we could possibly make. So let's go big to middle. B to E equals C to B. B to E equals A to F. Then C to B, here, AF. Okay, that's all from big to medium triangle. We'll call this the big triangle, the medium triangle, and the small triangle. Now let's go medium to small. Okay, E to F equals B to A. F to D equals B to A. E to F equals F to D. Okie dokie. Now we have to go big to small. And we're going to see that some of these proportions are actually the geometric means we are looking for. B to F equals C to A. Okay, B to F equals A to D. A to D. Now I'll put these two together. C to A equals A to D. So to get a geometric mean, let's look for any proportion in which there's a cross product where both letters are the same. Right there. That's one. Here's one where A is the same. And here's one where F is the same. If I were to cross multiply these, I would get B squared is equal to C times E. So I'm going to write this down on another sheet. I'm out of room. B to E equals C to B. Okay. C to A equals A to D. E to F equals F to D. Those are the three proportions I found. If I cross multiply them, B squared equals EC, or B equals square root of EC. A squared equals CD, or A equals square root of CD. You can work with them in any form. They're all equivalent. F squared equals ED, F equals square root of ED. If we go back and look at our original picture, we can see for this one, F is the altitude. It is the geometric mean between the two segments of the hypotenuse. It just comes from setting up similar triangles. This is just a shortcut to having to just break apart the triangles and do proportions until you get one that you can solve the picture. Then we have each leg as the geometric mean. A is the geometric mean between C and D, the hypotenuse and the segment connected to A. And then there's the B one. B is the geometric mean between the whole hypotenuse and E. Those are our theorems. So now we have these theorems that we can use to quickly solve problems. In a pinch, you can always go back, break the three triangles down, and if you cannot just know the theorems to use it and quickly get your proportion, you can go back and break it down and get the proportion you need anyway. Okay. So now our next video, we're going to do some problems with these.